All right, for this demonstration, we are going to do what's called Chemiluminescence. So you can see that my student is holding up two clear, colorless liquids, and when she mixes them, we're going to see that they glow in the dark. So to do this, we're going to have to turn the lights off. So we're going to have my student quickly turn the lights off, and then we're going to come back and see how they glow. All right, so she's moving the two liquids over to a funnel, and she's going to pour them into the funnel, and as they mix together, we see this beautiful blue glow, and it just looks fantastic, spelling out the word cool for us. So this reaction is called chemiluminescence. It's a chemical reaction that gives off light, whereas most chemical reactions give off heat. So this one's a little bit different. And now we're going to pour them into the second funnel, and we're going to see the other word come to life. And there goes the blue light into the word chem. Cool chemistry. Very, very fun, very, very cool. Beautiful blue light. I hope you guys enjoy this demo. Okay, for today's demo, we are going to burn ammonium dichromate, which is a fairly toxic chemical, so please don't try this at home. And we are doing it in a fume hood to ensure the safety of both my student and myself. She's pouring a pile of this ammonium dichromate onto this metal baking dish. She's going to make a little mountain of it. You can see it has beautiful orange crystals, but again, this is really toxic, so we don't want to try this at home. And then all we're going to do is use a propane torch to ignite this compound. And we're going to watch it burn. Ooh, look at how beautiful that is. And so you can see this beautiful color. We're going to slide the sash of the hood down to keep us extra safe. And we can see the burning of this ammonium dichromate. And it's quite beautiful, but again, remember, it's quite dangerous. It's making some chromium oxide compounds that have that green color, and it's being sucked away by the fume hood to keep us all safe, which is good. That's the point of a fume hood. But look at that beautiful volcano that we're making. Quite entertaining, very fun to watch. Do not try this at home. Okay, we are going to attempt to burn a gummy bear. So what we see in front of you is a test tube containing a salt, and this salt happens to be potassium chlorate. This is a salt that contains a lot of oxygen. So it's kind of similar to table salt, but it has potassium instead of sodium, and it has a lot of extra oxygens on it. My student's going to actually use a propane tank to start melting it. The reason that we want to melt it is because solids, they don't react very fast, but liquids react a lot faster than solids. So we need to turn this solid into a liquid, and it has a very high melting point, so we need a very hot flame in order to do this. So you can see the propane tank is slowly melting the solid that is in that test tube. Please don't try this demo at home. You would only want to do this under supervision of people who know what they're doing in order to handle these types of chemicals. Again, we're melting this solid into the liquid because the liquid is going to be more reactive. And once it's melted, we're going to put a gummy bear inside this test tube and see how rapidly it burns. It will only be one gummy bear, but you will be amazed at how quickly that one little gummy bear burns in the presence of this salt that has lots and lots of oxygen. So oxygen is going to promote the reaction, and it's quite fun. So I think that's probably pretty good for my student. He can get ready to turn that off and put that gummy bear in there. I'm also going to have him shut the light off on the fume hood. And now he's going to add the gummy bear. that was fantastic. So the purplish flame that you see is because of the potassium in this salt. And again, can you believe that's the burning of just one gummy bear? Quite spectacular. We'll be back for a second one in a second. And we're back, and this time we are going to use a different salt and a different candy. So inside this test tube is sodium chlorate. So same thing as the potassium chlorate, the only difference is a sodium metal instead of a potassium metal. My student is once again going to melt it using the propane tank because we need it to be in the liquid form instead of the solid form for the same reason, right? It's a solid, and solids don't react as fast. This one has a higher melting point than the previous one, so it's going to take a little bit longer to get it to melt. We're using the same propane tank in order to do this, have that high heat. Please don't try this demo at home. There's a lot of risk involved. We want to do this in a controlled manner with people who are experts and know how to, all the safety precautions. Again, this one's going to take a little longer to melt simply because it has a higher melting point, but it's going pretty rapidly because of the hot propane tank, so that's good. And when we're finished melting this salt, we're going to have my student turn off the lights again, and this time we're going to add a peanut M&M. So I want you to watch the burning of it really closely because the peanut M&M has 3 different layers, and they all burn a little bit differently. The candy shell burns that rapidly, it's almost done before you know it. Then the chocolate burns, and then we get to the peanut. And the peanut burns quite spectacularly, so keep your eyes peeled for those changes in the way things are burning as we add this peanut M&M. I think that's probably good enough, so I'm going to have my student turn off the tank, and then he's going to turn off the lights inside the fume hood, and then finally he'll add that peanut M&M. Wow, so hopefully you saw all 3 different types of burns, and also you noticed a different color than before. This is because of the sodium. The sodium imparts a color that's a yellowy orange. We hope you enjoyed that. Again, don't try it at home. Okay, we have an exciting demo for you right now. So my student is going to do what we call the Woosher bottle. So in his hand he has a small bottle of the Woosher bottle mixture, which is 2-propanol with some boric acid. Don't try this demo at home. And he has poured that liquid into the flask, and now he's going to swirl this giant flask to coat the sides, the insides of this flask with this liquid, and try to turn it into a vapor, because vapors, or gases, are more reactive than their liquid counterparts. Now he's going to pour out the liquid into this little beaker that we see, and what we want to do is we want to have the sides coated, but we also want to mostly just have the gas inside of the flask and not have any too much excess liquid inside. He's going to set the bottle down, and he's going to push that little beaker away, and now he's going to get his lighting stick. Again, do not try this at home. And we're going to try to ignite this liquid, and it may be loud, so just be warned. Again, this is the Woosher bottle. Awesome. All right, we hope you enjoyed that. Okay, for this experiment, we are going to react a cola with bleach. Please don't try this one at home because it actually does produce something fairly toxic. So what we see in front of you is just a large beaker filled with cola. And now my student's simply going to add a little bit of bleach to this, and you should be able to see the bleach basically strip the color out of this cola. He's going to add the bleach. You can see it reacting already. He's going to give it a quick stir to help it out a little bit, and it's just removing all that color via a chemical reaction. And you know, we all know bleach, it whitens stuff by stripping colors out of it. Again, don't try this one at home because it does produce chlorine gas, and that is toxic. We would not want to inhale that. So we are doing it in the safety of a fume hood. but you can see that it has stripped the color of the cola. Okay, for this demonstration, we're going to show you the power of this nitric acid, and then separately how we can neutralize it using the opposite of an acid, which is called a base. So to begin with, we have this very concentrated acid called nitric acid. My student is wearing gloves to ensure his safety. We would never try this demo at home, but we're going to demonstrate how strong it is by having him pour a little bit of this acid into a beaker that contains 1 penny. Okay, so he's going to carefully pour a little bit of this acid into this beaker, and it's going to start reacting with the penny in the beaker. You can see the green solution starting to form, and we can see that it's definitely going through what we call a chemical change. You may even be able to see a lot of bubbling occurring, and it's starting to fume, which is why we are doing this demo in a fume hood. You may even hear some background noise. That's the fume hood running. So we're going to slide that one backwards just a little bit, get it really away from us to keep us safe. The brown gas that you see forming is actually the main component of smog. It's a nitrogen oxide gas, and we don't want to breathe that in. So now what we're going to do is we're going to pour some base. This is sodium hydroxide. We're going to pour that into the beaker, the other beaker that has a penny in it. And then we're going to add some of the acid to that beaker and show that they neutralize each other and the penny does not react. So pour a little bit of that acid in there. They react with each other, but the penny will not be reacting because the base neutralizes the acid. And so you can see we don't see that bright green color, we don't see the smoking, and we see a little bit of bubbling, but that's just the acid reacting with the base, and so we can see how those bases neutralize the acid. Here is an overhead shot a couple minutes after the reactions have progressed, and you can see that the original one with just the acid is still reacting, violently green colored, brown smog still being formed, and the one with the acid and the base has stopped bubbling, and we have no green color and no smog forming because the acid and the base have neutralized. And so hopefully that gives you a great view of the difference between these two chemical reactions. Okay, we're excited to show you the rainbow flames. Don't try this one at home. My student is going to light each of these dishes that you see in front of you, and each one contains a little bit of an alcohol and then a clump of a different salt. There's lots of different salts in the world, and each one contains different metals and different what we call anions. The metals are what is going to impart color to these flames, and we hopefully have them in an order that is kind of a rainbow. You can see the alcohol is burning off, that's the bluish flame, and eventually it starts to burn the salt. And again, the metal part of the salt is what's imparting color to the flame, and we're starting to see this beautiful rainbow colored flame effect. So on the right, the far right, we have a salt that has lithium, and lithium gives off this beautiful pinkish reddish flame. Then next to that we have strontium, which is a reddish orange flame, and next we have sodium, which is a yellowish orange flame, followed by boron, which is a green flame. Next we have copper, which is a blue-green flame, followed by barium, which is a bluish flame with some orange in there, and then finally potassium on the far left, a purple flame. So we'll let this record for a while so you can enjoy all the beautiful colors. Again, please don't try this one at home. Okay, we are ready to try the thermite reaction. First of all, don't ever try this one at home, but we're going to attempt to do the thermite one here safely in our fume hood. So the first thing my student is going to do is try to light the two separate ingredients, which are aluminum powder and iron oxide powder. And we're going to do this by using a sparkler to show how much heat and energy is required to initiate these reactions, but what you'll see is that the two don't really react by themselves. So I'm going to have him light his sparkler. And now he's going to attempt to light the iron oxide powder, which is the red one. This is basically like really pure rust. And you can see nothing's happening. Just a sparkler, not igniting that other pile. Now we're going to try to light the aluminum powder. Again, nothing happening, it's just the sparkler, right? So these two ingredients separate don't really do much. And they're solids, which are usually not very reactive. Okay, so now we're going to attempt to burn the thermite. And so we're going to initiate it with the sparkler, just like you saw before. But now inside the pot is, of course, a mixture of the two components. Again, the aluminum powder and the iron oxide powder. It needs a lot of energy to get it going, which is why we use a sparkler for this. Again, do not attempt this at home. Ooh, that was spectacular. And there we are, the thermite reaction. It even is so hot that it makes molten iron. I'm going to have my student tip the ring stand forward towards the camera in the hopes of maybe seeing a little bit of the iron that is formed. And actually it looks like this one was so rapid that we just got little tiny bits of iron and not a big chunk of iron. But this is one of the ways that they welded the railroad ties together. Oh, there it is. Oh, look at that. An amazing ball of iron. It's really hot, which is why it's still glowing red, and that's why we have all the sand around to cool it off quickly. Again, the thermite reaction. We hope you enjoyed that. Please don't try this at home. Okay, for this experiment, we're going to work with a mixture of dry ice and acetone, which you can see in this big bowl in front of us. When you mix these two things together, it makes a mixture that is extremely cold. It's actually negative 109 degrees Fahrenheit. And so we're going to work with this really cold mixture, playing with some different things. Don't try this at home. It's really, really dangerous because of how cold it is. Also, I want to mention that inside the container are some flour bits from practicing this demo. And so you'll get to see what that does at the end. So my student's now going to place a balloon that he inflated with his breath. He's going to place this balloon inside this very, very cold mixture to try to cool the air that's inside the balloon down. And so he's spinning the balloon around, and you can already see that it's starting to shrink. So why is the balloon shrinking when it's in this cold environment? Well, when molecules are cooled down, they like to come closer together. And so that decreases the volume of the gas that's inside this balloon. And again, this mixture is so cold that it's greatly decreasing the volume of the balloon in this really, really cold environment. And now what he can do is pull it back out, and we can watch it warm up. And as it warms up, it's going to start to re-inflate back to the size it was before it was cooled down, because again, the molecules are warming up. They start to expand, we get this greater volume, and it's really kind of a cool visual effect. So now what we're going to do is we're going to place a rose inside this very cold mixture, and we're going to try to freeze the petals. So you can even hear the bubbling that's going on as we freeze these flower petals. You can hear it sounds almost like glass. And now we're going to pull it out, and we're going to push the beaker away, and we're going to shatter this flower. Fantastic. Okay, we are about to attempt the blue bottle experiment. So inside of this flask, we have a mixture of potassium hydroxide and dextrose, aka glucose, D-glucose. And when these two things react, they are going to eat up oxygen. In order for us to see this more visually, we're going to add an indicator. This indicator is called methylene blue. My student is going to add it to the flask now. We're only going to add, 6 or 8 drops of this. It's quite a beautiful blue indicator. And so what we should see as the reaction progresses and uses up the available oxygen, the blue color of the indicator should go away. So she's going to stopper the flask and shake it up just to get that blue mixture in there fully. And Again, the oxygen in the bottle, the oxygen that's present, should start to react away. And so we're going to actually just let it sit. And we should see the blue color go away as the reaction progresses and eats the oxygen up. So we're going to have some patience. This takes just a little bit of time. Oh, you can see it happening already. There it goes, the blue color going away because the reaction is eating up the oxygen. There's just a little bit left at the surface. That's because that's where the oxygen is most abundant. And so now what we're going to have her do is shake it up again. This should introduce oxygen back into the reaction, and so it should turn back into the blue color, because again we're adding oxygen by swirling around with the gas that's in the flask, and there's the blue color back. And now we're going to let her let it sit, and when we let it sit, the oxygen gets reacted away, and we should see it slowly turn back to colorless. There it goes. How beautiful is that? So we're going to do this 1 or 2 more times just because it's so cool. You can do it multiple times. It will eventually wear out. But let's have her shake it up again. Again, we're introducing oxygen into the system by shaking it up. The oxygen that's above the liquid level but still contained in the flask. And there's that beautiful blue color back again. And then we'll let it sit. You can see the color already going away. Let's do it one more time. She's going to shake it up, introduce that oxygen into the system, see the deep blue color come back, and then we'll let it sit one last time, let the reaction proceed, let the oxygen get eaten up, and the indicator tone turn back to colorless. And again, this is the blue bottle experiment. We hope you enjoyed this one. Okay, for this experiment, we are going to attempt to mix 3 different solutions together, and we should see some pretty color changes. Okay, for this experiment, we are going to play with invisible inks. My student has 2 different inks that we're going to test today. The first one is a mixture of baking soda and water, and I'm going to have him go ahead and dip a Q-tip into the baking soda and water and then write a message on his piece of paper. So he's just getting a little bit of that solution, and then he's going to write his message in invisible ink. Remember, this invisible ink is a mixture of baking soda and water. And now he's going to write a second invisible ink message using lemon juice. And now we're going to let these papers dry, and when we come back, we're going to reveal the secret messages. Okay, we're back, and our messages are mostly dry, so we're going to reveal the first message using grape juice. Remember, the ink was a mixture of baking soda and water. We're going to reveal it with grape juice because grape juice is dark and purple, but also because it's acidic, and baking soda is basic, so there's going to be an acid-base reaction taking place here. Oh, and you can see the blue color of the words coming through with the pink of the grape juice. How cool is that? It says cool. And now we're going to reveal the lemon juice one using heat. So I have a hot plate here in front of me. My student's going to place the piece of paper on this hot plate, and it's going to warm up the ink. Remember, it was lemon juice. It's going to heat that lemon juice. The acid in the lemon juice is going to burn ever so slightly and turn the paper yellowish brownish and reveal our hidden secret message. Watch carefully and have some patience. You can slowly start to see the yellow of the words appearing. Can you see what it says? I think it says CHEM, but I want to see that M come through a little bit more. Yep, it's starting to work. That looks really cool. It says Cool Chem. Yay!
Alright, for my demo, it has to do with air pressure and how you can get a hard-boiled egg inside a bottle that it doesn't actually originally fit in, given that when you take the air pressure out of the bottle using the flame, because it uses up the oxygen, and the air pressure outside of it is normal, it'll push it inward without actually breaking it. And so long as there's a bit of a flame, it should suck it in. Hopefully now it works. Hey, there we go.
Okay, for this demonstration, we are going to try the elephant's toothpaste demonstration. We're going to try a version that you can do at home. So the ingredients in front of you are things you should be able to acquire. On the far left, we have a beaker of 3% hydrogen peroxide. This is the stuff you can get at a pharmacy, and you can maybe use it for your cuts. And so my student is going to slowly pour that into the bottle. He has a funnel at the top to help him out. You can use about a cup of that, maybe a little less than a cup. The next ingredient is food dye. You can use any color you like. My student is choosing green, but it's your demonstration. You can choose any color that you want to use. And the next ingredient is some dish soap. So we're just going to squirt a generous amount of the dish soap into the solution. Any dish soap will work. And then he's just going to swirl that all around to get it nice and mixed without making too many bubbles. Now what we're going to do is mix some active yeast, again something you can buy at the store, with some warm water to try to activate that yeast. You may be able to see it bubbling a little bit. It's definitely starting to activate. And now that is going to be the catalyst for our reaction. And a catalyst is simply something that makes a chemical reaction happen faster. So the reaction that my student's about to perform, again the elephant's toothpaste, is simply a decomposition of hydrogen peroxide into oxygen gas and water. So let's see what happens as we add this activated yeast to this hydrogen peroxide solution. So you can see a small amount of foaming starting to occur. The solution is growing because we've added this activated yeast that's making a lot of oxygen gas form. The oxygen gas is mixing with the soap and making foamy bubbles. It's slowly starting to grow. And we're just going to have patience and watch. The rate of the reaction, which is another word for how fast it occurs, depends on how active your yeast is and also how fresh your hydrogen peroxide is. And so you can see that ours is pretty slow. Our peroxide might be a little bit old, our yeast might be a little bit old, but again, you're seeing a chemical reaction happen, and it's just a little bit slow. It's getting close to the top now. And there it goes. The elephant's toothpaste demo, pouring out just like toothpaste. Pretty fun. We're going to be back with a more exciting version of this in just a second. Welcome back. We're about to try the Elephant's toothpaste demo again, but this time we're going to be using some stuff that you can't get at home, and please don't try this version at home. This is only for people who are trained and know how to use these more hazardous chemicals safely. So this time we're going to be using 30% hydrogen peroxide, not something you can get in the store. My student is going to make sure he's wearing gloves, and he's going to pour about 100 milliliters into this flask. Again, do not try this version at home. 30% hydrogen peroxide is 10 times stronger than the stuff that you can get in the store, and it really burns if you get it on your skin. So you want to take lots of PPE precautions to keep yourself safe. We're still going to add the food dye, just like we did the first time. My student has chosen green again. And we're still going to add the dish soap, just like we did before. Good, healthy squirt. And just like before, we're going to swirl that around, get it to mix, but not create too many bubbles. And this time, the catalyst, remember that's a word for something you add to a reaction to make it go faster. This time the catalyst is potassium iodide, or Ki. It's dissolved in water, and we're just going to add a bunch of it and see this reaction go. Elephant's toothpaste. You can see how much faster it is. Grow. Isn't that fantastic? So I hope you guys all enjoyed the bigger version of Elephant's toothpaste. Okay, for this demo, we are going to make a density column. And what that means is that we're going to layer up different liquids of different densities, and they should sit on top of one another the lighter the density is. So we're going to start with a really high density, a really thick, viscous liquid. We're going to start with honey. This, again, is a very thick liquid. The word in chemistry that we use is viscous. That means that the liquid is very, very thick and pretty resistant to flow. And you can see that it takes a while to pour all of that honey out of that cup. And again, this is the most dense liquid that we're going to be using in this density column. The second liquid that we're going to be adding is corn syrup, but this corn syrup has been dyed red to make it a bit more visible and to have a clearly different color than the honey. Again, pretty viscous, but not quite as dense as the honey, which is why the corn syrup is sitting on top of the honey. The third liquid that we're going to use is dish soap. This dish soap happens to be blue, but you can use lots of different dish soaps. Again, and dish soap is a pretty viscous liquid. It's not as viscous as honey. It's also not as viscous as the corn syrup, but it's still pretty viscous. You can see that it pours pretty slowly, and it's less dense than the previous two, and that's why it's sitting on top. And it has this really pretty blue color. So we're getting these really, really beautiful layers. The fourth liquid that we're going to use today is actually water. And the water we're going to leave as colorless. We're not going to add any food dye to it. And it is less dense than the dish soap we've been working with. And we need to add it in a slow and controlled manner. So my student is going to be using a turkey baster to help her out with this. We want to slowly run the water down the side of the flask so it doesn't mix too quickly with the soap below it. So you can see that she's doing this in a very slow, patient manner in order to get the water to sit on top of the dish soap and not. The fifth liquid that we're going to use is vegetable oil. So this vegetable oil we're leaving just the way that it is. It's kind of a pale yellow color. Most of us know that oil is less dense than water, and that is why it sits on top of water. And so again, my student is going to use the turkey baster to slowly add the vegetable oil to this density column. We have to do this very carefully to ensure that the liquid stays on top and doesn't mix with the water. Okay, the sixth liquid that we're going to add to this density column is rubbing alcohol, like you can buy at the store. And we have dyed it green in order to give it a distinct color different from the water. And again, the rubbing alcohol is much less dense than water, and it's also less dense than vegetable oil. It's very low in density. It's not very viscous at all. And again, we're going to add it very carefully using the turkey baster, dripping it down the sides so it doesn't accidentally mix quickly with the oil or even get below and get into the water. And the final liquid, the seventh of this density column, is lamp oil, which we're also leaving colorless. It is the least dense of all the liquids that we're adding to this column. It's very low in viscosity. It's a very thin liquid. And we're going to use the turkey baster one last time in order to add this carefully to our density column. And then when we're done with it, it should be complete. And there we have it, a very beautiful 7-layer density column. Again, the bottom layer is honey. The second layer is corn syrup dyed red with food dye. The third layer is dish soap. The fourth layer is water, not dyed. The fifth layer is vegetable oil, again, not dyed. The sixth layer is rubbing alcohol, dyed green. And finally, the top layer is lamp oil, not dyed. We hope you enjoyed this really cool density column. Okay, we are going to attempt to make slime, all kids' favorite chemical reaction. So what we see and sitting in front of you is a mixture of 4% polyvinyl alcohol, which is a really long molecule, and it's kind of slimy already, but not slimy enough. So in order to make it a little thicker, we're going to add 4% borax solution that's been dyed with green food coloring. So my student's going to actually add that in right now, and then he's going to stir it up, and the borax is actually going to do a process called cross-linking. So cross-linking means to take these long chains of molecules and link them in the middle at all sorts of different parts, kind of like a chain-linked fence. And when the molecules cross-link, they get thicker and tighter and more slimy-like. And so now we've made some beautiful slime, and my student's going to pull it out of the beaker and play with it for you all to see up close and personal. So there's that lovely green slime that everybody loves to play with. All right, see how stretchy and gooey, thanks to all that cross-linking. It's a much tighter molecule now with all that cross-linking, and that's the nature of slime. Most slimes are just cross-linked molecules, whether the slime comes from glue or polyvinyl alcohol or other molecules. And again, these are polymers. Polymers is a word for very large molecules. So if you like slime, go ahead and play with slime at home. It's a lot of fun, and I hope you enjoy it. Okay, for this experiment, we're going to attempt to extract the DNA out of strawberries. So what we have in front of you is a bag full of salt, shampoo, and water that's been mixed with a crushed strawberry. And so that is going to help to pull the DNA out of the strawberry, and my student has pre-crushed all of this stuff and mixed it together in this baggie. So now she's going to pour it onto this funnel that has a cheesecloth on top. Basically, this is to separate out all the chunks and be left with just the liquid that we have from the strawberry. So you can see how she's squeezing the chunks and letting the liquid run through into the test tube below. This is a really fun experiment that you can try at home. It's a little bit messy, but it's worth it. So again, we're just going to squeeze some more of that mixture to try to get as much liquid out as we can, leaving all the chunks of strawberry behind. So why do we choose strawberries for this experiment? Well, we choose strawberries because they actually have 8 copies of their DNA chromosomes, whereas humans only have 2, and so we wouldn't be able to get as much from, say, a cheek swab as we can get from this strawberry. So it's kind of a great creature to study, investigate its DNA, all of that great stuff. So now we've collected quite a lot of strawberry juice, and so now my student is going to add in some cold isopropyl alcohol, and this should pull the DNA out and bring it to the top of the test tube. She's going to pour it very slowly down the side in the hopes of things beginning to separate. So isopropyl alcohol is the alcohol that's in rubbing alcohol. So if you were to try this at home, you could try rubbing alcohol. We're using pure isopropyl alcohol, which means it has no water in it. And that is a bit more effective. And now she's just going to use some tweezers and start to pull the DNA out. And there's the long strings of DNA. It is a polymer, which is a word for a large, long chain molecule. It's a biopolymer, so it comes from living creatures, and it's a very, very large molecule. It kind of has a property like slime, because slime is also a polymer, and there we have the beautiful DNA extracted from strawberries. Okay, for this experiment, we are going to try to make some water balls. So to do this, we're going to add some sodium alginate to the dyed blue water that you see in front of you. So the sodium alginate is this little kind of off-white powder that my student is adding to this water that we've dyed blue, and he's going to mix that around really good to try to get it to dissolve. It's a little bit hard to dissolve, so it's going to take a little bit of time to mix that all around and get it really, really dissolved in that water. And after he's done doing that, he's going to add the other powder, which is more white. This is calcium lactate, and he's going to add that to the water that has not been dyed. So it's clear, colorless water. We're going to have him stir that up really good and try to get that calcium lactate to dissolve. That one is a little bit more soluble in water, so it dissolves a little bit more quickly. Okay, we've let this sit for a little while, and now we're going to try to make a water ball. Carefully dunk it into the solution, and we kind of have a water ball. So my student is going to very carefully try to show you all what we've got there. It's a little bit like slime, but it does kind of trap the water within it, and basically the two chemicals don't want to mix because they've made what's basically like a plastic, except it's made out of stuff that comes from nature, so we would call it like a biopolymer. And it's kind of slimy, and it's really cool, and this is definitely something you could try at home if you can get your hands on the correct ingredients. And here's the final result, a water ball. And now my student's going to prove by popping it open. There it goes. So the water was trapped inside, and we made this cool gelatinous ball that's basically like a slime ball with water trapped inside. Okay, for this demo, this is one that you can try at home. We are going to make a homemade lava lamp. So the first thing that we're going to do is pour some water into the bottle. You can pour it, or you can use a funnel to do that. And again, this is just regular tap water. You can use water from your sink and just pour it in until the bottle is about a quarter of the way full. Basically, just towards the, have the bottom mostly full of water, and that looks really good right there. Then you can dye that water with any color food dye you like. So my student has chosen blue, but if you like red or green or yellow or any of the fun other food dye colors, you dye that water up any color that you like. So add a few drops and then swirl it up in order to mix it all up and make sure that water looks really, really good the way that you like it. Now you're going to want to have a grown-up help you. We're going to put the funnel back on the bottle, and we're going to slowly add a bunch of vegetable oil. So you want to keep adding vegetable oil until the bottle is about 3/4 full. So mostly full, not all the way full. And you're going to see the oil and water are mixing, but they don't really like each other very much. They have really different chemical properties. So slowly, they're going to separate, but it's going to take some time. So we are going to pause the video here, and we're going to come back after the oil and water have fully separated. Okay, we're back, and we have let the water and oil separate into their two layers, and now we're going to add the effervescent tablets. What you should see is the tablets sink to the bottom into the water, And when they get to the water, they're going to start to dissolve. And when these tablets dissolve, they release carbon dioxide gas. That gas really wants to escape the bottle, but the only way it can is by passing through both the water and the oil. And as they go up, they're grabbing globs of water with them. The water is colored so we see it, and it doesn't want to mix with the oil well, so it looks like a lava lamp. So this is a homemade lava lamp that you can make at home. And another cool thing about it is that you can do this experiment lots of times, not just once. So when it's finished and it's all done bubbling, you can put the cap back on, put it on your shelf, and the next time you want to try it, take the cap off, put some new effervescent tablets inside, and it should work all over again. Every time you add new tablets, it can keep working. It's a really fun demo, great for little kids. I hope you guys enjoy trying this one at home. Okay, for this experiment, we're going to investigate two different sands. So one is regular beach sand, and the other we have done a chemical process on it. So we're going to start with the regular untreated sand. My student is going to pour it into the beaker on the left, and you should be able to just see the sand go into the water like normal. And, you know, just watch it closely, see what the sand does, right? It just goes down, it kind of disperses a little bit, almost looks like a cloud. My student's going to swirl it around a little bit. And, you know, it's sand. If you've been to the beach, you know what it's like, right? It sinks to the bottom, and that's about it. Well, now what we're going to do is we're going to look at some magic sand. This is homemade magic sand. We've sprayed it with boot waterproofer. So this is something you could try at home. You just spray a bunch of sand with this boot waterproofer, and it will turn into magic sand. So when we pour it into the beaker, we should see it do something very different. See how it's clumping up? It doesn't really want to mix with the water. The boot waterproofer is making the sand hydrophobic. That's a word that means fearful of water. It does not want to mix with the water. It wants to clump up and stick together and be away from the water as much as possible. It's kind of fun. It's great to play with. So again, if you want to try making this at home, all you need is some boot waterproofer and the sand. There's also some practical applications for this. You can use this hydrophobic sand to clean up oil spills, and this is one of the ways that in the environment we can try our best to clean up oil that has spilled, because the chemical that is used in the boot waterproofer actually likes oil a lot more than water, so it will suck up the little drops of oil and help clean up those things. So a great demo, something to try at home. All right, for this experiment, we are going to be investigating the pH of acid rain and hopefully looking at one solution, which is using limestone in lakes to help neutralize the acid rain. So we have this pH indicator color strip, and the acids are very, very red, and the bases are very, very purple. We're hoping to get to like a green, neutralish color. And inside the tube you see in front of you is a bunch of calcium carbonate chips, which are basically chunks of limestone, and they act as a base to react with any acid that we're going to add to this system. So my student is going to add some very acidic solution to the top of this tube, and you can see that the solution is bright red because it's been dyed with this indicator. And so she's going to slowly pour this into our setup, and we're going to start to see this acidic solution slowly drain through the tube that has these calcium carbonate chips. And you can see the color changing as the solution moves through the tube. So you can see that it's starting very, very acidic, but as it gets about halfway through the tube, it's starting to become more like pH 5, and then by the bottom, it's close to pH 7, which is neutral. So these chips are doing their job. They are neutralizing the acid and turning this really acidic solution into something that's more pH neutral. So again, this is a great example of environmental chemistry and a way that we can combat a negative effect that we see in the environment of acid rain. For this demonstration, we are going to use red cabbage juice as a natural acid base indicator. This is something you can try at home, and so my student has made this purple juice from a red cabbage by chopping it up, throwing it in a blender with a bunch of water, and then straining off all of the pulp using a cheesecloth to get just this beautiful dark purple juice. And now we're going to use it as an acid base indicator, which means it's going to change color based on the pH of the solution it's in. We're going to start with one extreme, which is a strong acid called HCl. So my student is going to pour some HCl, or hydrochloric acid, into the first beaker. And hopefully you will see a nice color change to indicate that it is an acidic solution. Fantastic. Look at that bright pink color that we see. So that's the color that red cabbage juice changes when we have a strong acid. Now she's going to do the opposite of an acid, which is a strong base, or sodium hydroxide. She's going to pour this into the second beaker, and we should see a color change. Great. It turned to a dark green color, and so that's the color of this red cabbage juice indicator in base. She's going to move that beaker all the way to our far right-hand side, so we now know what the colors are of the two extremes of this acid-base spectrum. So now we're going to have her pour in some baking soda. So this is just baking soda you can get from any store, and we're going to add that to one of these beakers and see if it's an acid or a base. While she does this, why don't you guess what's going to happen? Is it an acid or is it a base? Give it a stir, see what happens, maybe add a little bit of extra. And we see it turn blue, almost turquoise, so baking soda is a base. We're going to have her move that to the base side of our fume hood here. Alright, let's try some tonic water. While she gets the tonic water ready, I want you kids at home to guess, is this going to be an acid or a base? Let's have her pour some tonic water into the beaker. Ooh, it's really acidic. Look at how bright pink that is. So we're going to have her move that beaker to the acid side of our spectrum here. All right, we have two chemicals left. Let's go with vinegar. So again, something you can try at home and test all sorts of different things that you have at home. She's going to pour a little vinegar into one of these beakers. And again, it turns pink. So a vinegar is also an acid. So we're going to have her move that beaker to the acid side of the spectrum. And the last chemical we're going to test for you today is bleach. So she's going to pour some bleach into this last beaker. Is it going to be an acid or a base? What do you think? Ooh, look at that. It turned yellow. That's a really strong base. It's almost as strong as the base that we used to begin with. You can see they have almost the same color right now. And so that is a great demo for you all to try at home. Red cabbage juice as a natural acid-base indicator. You can test all sorts of fun things that you have in your house. For this experiment, we're going to explore the concept of a buffer. So the buffer we're using is milk of magnesia, which is something you can buy at your pharmacy, and it's a white suspension of powder in water, and you can take it if you have a stomachache. We have that solution in our flask, but we've added universal indicator, which is the other bottle on your right, and that is a pH indicator that changes color depending on the pH of the solution, and you can see the color key next to our flask. So this buffer is actually pretty basic. It's very high in pH, about a pH of 10. We're going to see how this buffer reacts to the addition of acids, which are very red on our scale. So we're going to add some 1 molar hydrochloric acid, and we should see a color change. There's the red, but look how it immediately goes to green and then maybe even back to blue. This is because a buffer is resistant to pH changes, so it keeps wanting to go back to its original pH. Demo, we have something new and exciting for you all to see. It's called the chemical aquarium. So what we have in front of you is a dish full of what's called water glass, which is a solution of silicon dioxide dissolved in water. And silicon dioxide is actually a component of glass, so that's why this is called water glass. My student is going to add some crystals of various salts to this that have a lot of color. The first one she's going to add is orange, and it is an iron 3 chloride salt. There it is, beautiful. She's going to add that in various places. Looks so pretty, and you might start to see something happen. As we wait for that to happen, we're going to add some nitrate crystals. These are kind of green. Nickel nitrate or nickel 2 nitrate. Ooh, there we go. We're starting to see things grow. See the vines growing off of these crystals that we're adding to the dish? Isn't that neat? The next one is a very faint pink called manganese sulfate. And again, just keep your eye on what's happening to these crystals as we drop them into the water glass. So pretty seeing these vines grow. And the last one that we're going to add is copper 2 chloride or cupric chloride. It's a turquoise, a little bit more blue than the nickel one, but very similar in color. And again, you can see these beautiful vines growing. You can think of it like vines in jungle or like seaweed growing, but it has this beautiful effect as it dissolves into the water glass. And we see little bits of the color sort of suspended. It's quite pretty. Not something you can try easily at home, but something very fun to watch on our Cool Chemistry video here. And maybe someday you can come and be a student here and you can do a demo like this yourself. I hope you enjoyed this one. Okay, for this experiment, we are going to try to make instant snow. So inside of the beaker in front of you, you see something called sodium polyacrylate. That's a big fancy word for something that's a polymer, which is a really, really big molecule. And this molecule in particular really likes water, and it can absorb a lot of water, but when it does, it turns into big puffy things that kind of look like snowflakes. And they even use this sometimes to make fake snow in movies. So my student is going to pour in some water into the flask, and we're going to see this instant snow happen. Now watch closely, it's growing. It's absorbing all that water, and the molecules are starting to grow, and now it's looking like snow. Isn't that cool? Instant snow. I hope you guys thought that was fun. Alright, for this demo, we are going to try to crystallize a solution of supersaturated sodium acetate. So my student is slowly going to pour it onto the crystals of sodium acetate. And we should see it start to crystallize and basically turn from a liquid into a solid. It is definitely starting to crystallize. Yeah, let's keep going. That looks good. So you can see the crystals starting to form on the dish. So a supersaturated solution means that there's a lot of the crystals dissolved in the solution, and it does not like that. And so it wants to come out of solution. That's called precipitation. And as we pour the liquid, it starts to crystallize and form all these crystals on the dish that you see in front of you. And you can see that it's even forming crystals inside of its own beaker. And there we go, the crystallization of supersaturated sodium acetate.